let's begin. We might have some people trickling in later, but I hope everyone is doing well. My name is Vincent Guan, and I'll be moderating our first session of the Minisymposium that we have here on SIAM for learning from data with information theory and causal inference. It'll be a 2-hour session. We'll have 4 different talks, each roughly 25 minutes with 5 minutes or more if there's room for discussion. And our first speaker I'd like to invite is Dr. Ryan James from UC Davis, who will be presenting the dependency diagram, a new method of understanding interdependence in multivariate distributions.
Thank you. Sorry. Thank you. It's a little early for me. I'm normally in a different time zone, so bear with me if I speak a little slowly. At first, I wanted to thank the organizers for inviting me and everyone for showing up to this mini symposium. It sounds like it's going to be exceedingly interesting, so I'm really looking forward to the next few talks. But I will be talking about, as Vincent said, the dependency diagram. This talk will start with me going over some background on information theory and specifically multivariate measures of mutual information and kind of highlighting why they are not sufficient for understanding multi-way information interactions within distributions. Then I will dive into the contribution here, which is the dependency diagram, and we'll look at it for a few select distributions, and that'll be it. So hopefully it'll be relatively straightforward and provide a good background for any other information theory talks that may come up later. So without further ado, let's dive in. So defining fundamental information measures. First, there is the entropy, which is defined as the sum of P log P over a probability distribution, where P is the probability of each event. Log base 2 is taken, we just sum them up, and it gives a measure of uncertainty with the outcome of a distribution. So the more the more diversity in the outcomes, the larger the entropy will be. The more certain the outcome, the lower the entropy will be. You can do this for multiple or multivariate distributions, where the overall entropy of the distribution is given by the exact same formula. You just use a joint probability distribution rather than a single probability mass distribution. And then we can talk about what's known as the conditional entropy, which is the uncertainty in one variable given knowledge of the outcome of another variable. So in this case, we have variables x and y, and h of x given y is the amount of residual uncertainty in x once you know the outcome of y. So if we had 2 completely fair coins that we flip, the conditional entropy of one of them given the other will be 1 bit because the outcome of one coin doesn't influence the outcome of the other. Whereas if these coins were perfectly correlated, it would be 0 because once we know the outcome of one of the coins, we immediately know the outcome of the other one. The counterpoint to conditional entropy is the mutual information, and that is the amount of, well, that should be a minus over there. I apologize. But it is the amount of uncertainty sort of contained within both variables, or put another way, it's the amount of uncertainty that's reduced in one variable when given the other. Turns out this is a symmetric measure, which is very convenient, but it's fraught with multiple difficulties when moving into the multivariate setting and also when trying to leverage that shared information. I won't get into it in this talk, but the important aspect here is that there is the mutual information between x and y, it cannot itself be represented by an auxiliary variable. It's often in kind of an intangible quantity, and there's a suite of measures known as common informations, which do try to capture the mutual information in the form of an auxiliary variable, given various compromises. If anyone's curious about that, we can talk about it later. And one nice thing here is that these information measures can be represented with a Venn diagram, which is actually going to be a key component toward the end of this talk. But for now, we can kind of represent those information measures here, where this left circle represents the entropy of the variable x. The right circle represents the entropy of the variable y. Their intersection is represented by the mutual information between x and y. And then the two wings here on either side are the conditional entropies. Any questions so far? Cool, great. Once we shift to the multivariate setting, we can add one more measure here, which is the conditional mutual information. So that is the amount of uncertainty remaining between variables x and y once you know the variable z. So for example, well, we'll get to some examples shortly. And based on this additional measure, we can kind of, similar to the conditional entropy, we can talk about a mutual information measure. And in this case, it's known as the co-information. It's a symmetric quantity between x, y, and z that kind of represents the overlap of all three variables. Although interpretation of this quantity can be difficult, which we'll get into shortly. Again, these quantities can be represented on a Venn diagram, which we have here. We've just added a third circle, and now we have the three exterior components being the conditional entropy of x, y, or z given the other two. We have the conditional mutual informations as these kind of chevron shapes here. And in the very center, we have the co-information. All right, so let's take a look at what different quantities here look like for some example distributions and various ways of taking the mutual information and extending it to three or more variables. So the first distribution I'd like to work with for the remainder of this talk is called the copy bit. If we look at the probability mass function up here, we have values x, y, and z, or variables x, y, and z taking on values 0 or 1 with these specific combinations and probabilities. And with a little consideration, we can see that x and y are always identical, and they are independent from variable z. And if we look at the information diagram down here, that Venn diagram, we'll see that z, given x and y, there's one bit of conditional entropy there, which is represented by the independence of z, that coin flip that is unrelated to x and y. And the conditional mutual information between x and y given z is one bit, representing the one bit of information that x and y share to their correlation, and that it is divorced from the variable z. So at least in this situation, the Venn diagram feels very interpretable given the distribution. We can kind of infer one from the other very simply just by reasoning about the mechanisms within the distribution. Another distribution here is what we call the giant bit. In this case, x, y, and z are all perfectly correlated. They're all 0 simultaneously or all 1 simultaneously with equal probability. And in this case, the co-information is 1 bit and every other information measure here is 0, which again feels fairly interpretable. We say that the giant bit is one big coin flip. That coin flip is identical to the X coin, the Y coin, or the Z coin, and so it kind of lives in the center of this Venn diagram. So far, so good. The Venn diagram feels interpretable. But then we get to this other distribution, the exclusive OR. In this case, X, Y, and Z are either all 0 or exactly two of them are 1 and the third is 0, all with equal likelihood. And in this case, when we work out the information diagram, what we'll find is, for example, let's say we know the value of z is 0, then we find that x and y share one bit of information. They are perfectly correlated once we know the value of z. And so these conditional mutual informations should be one bit each. But if we look at x and y ignoring the variable z, we'll see that they're just two independent coin flips, just completely independent. And so their mutual information should be 0. To make that work out, this co-information must be -1. And I don't know about everyone else, but I have difficulty interpreting what a negative information should be. And so we've kind of hit a bit of a road bump where the interpretability of this Venn diagram has gotten a bit more difficult now. And finally, one more distribution of interest here. Sorry, is the Zoom window kind of overlapping part of the talk? I've seen that happen sometimes. No? Okay, great. We call this the W distribution. It comes from quantum information theory, where two of the primary forms of entanglement discussed are the GHZ state, which in this case is actually equivalent to the giant bit, and the other is this W state. In this W state, what we see is that one of the three variables is 1 and the other two are 0, each of the three possibilities equally likely. In this case, the co-information is negative here. It's a little, I wrote it exactly, which makes it a little difficult to know the sign, but in this case, it's about negative 0.4. And the conditional mutual informations are all 2/3. And we can see why that's true. For example, if I know that Z is 0, I know that X and Y are perfectly correlated. They are opposite of one another. I just don't know which value they have. So there should be this conditional mutual information. And if we look at the mutual information between X and Y, ignoring Z entirely, well, they're not entirely independent. Some of the time we know that they are correlated, but the rest of the time they're anti-correlated. It's just we don't know which of the two cases it is. One of them occurs 2/3 of the time and the other 1/3 of the time. And so we end up with some mutual information, but not a full 2/3 of a bit. And so in this case, that co-information is going to be negative again. But we're going to see that the negativity of the co-information in the case of the W state or the W distribution is very different from the negativity of the XOR as we get into the next few slides. I just want to pause for any questions that may have come up. None? Okay, cool. All right, so moving on, let's talk about ways of defining the mutual information. So the mutual information between variables just x0 and x1, or as we used previously, x and y, can be defined as the entropy of the joint distribution minus the co-information or the conditional mutual information of each variable given the others. That's one way of defining the mutual information. In that case, when we look at this picture here, it's the whole distribution minus, or the whole Venn diagram minus these two wings on the side, and we're left with the center component. Another way of doing it could be the sum of each individual entropy, so each circle, minus the full Venn diagram. A third can be this inclusion-exclusion sum, where we add components of the Venn diagram. So maybe in this case, if alpha is equal to 1, we're talking about each individual variable. And in that case, this sign is going to be positive, and that means we add each individual circle, but we're going to subtract each pair of circles, the three pairs xy, xz, yz. But then we add the full Venn diagram again. So we kind of do this inclusion-exclusion where we add or subtract subsets based on how many components are in them. And that it turns out to be equivalent to this mutual information. And a third is this kind of weird form, or a fourth is where this weird form where we look for the minimum value gamma such that the full joint entropy of the joint distribution minus gamma is equal to the sum of each individual entropy minus gamma. And it turns out that is another way of defining the mutual information. With two variables, all of these are completely equivalent, but as we move into 3 and more variables, they diverge. Oh, and there's another one here, which is the entropy of all but one minus the full joint entropy. So let's take a look at what these look like in terms of the Venn diagrams. This form where it's the joint entropy minus, or each of the individual entropies minus the joint entropy is called the total correlation. And for our 4 example distributions that we've been working with, for the copy bit, it's equal to 1, which comes from this conditional mutual information up here. The giant bit is 2, because in this case, the shading here is relevant to how many times each region of the Venn diagram is counted. And in the case of the giant bit, the center region is counted twice, which is where the information for the giant bit is. And so we get 2 bits for the total correlation. For the exclusive OR one, we had a negative in the center and 1 in the 3 conditional mutual informations. And so we have 1, 2, 3 minus 2 being 1. And for the W, we have some value, which is positive in this case. For 4 variables, the Venn diagram might look like this. And we can see basically the centermost region is weighed more heavily, and then as we move outward, the regions are weighed less and less heavily with this measure. So it kind of emphasizes the center of the Venn diagram, whatever that may mean informationally, and um, uh, areas where fewer variables are involved contribute less and less. Second, we have the dual total correlation given by the joint entropy minus each of these conditional entropies. And in this case, the copy bit is 1, the giant bit is 1, the exclusive OR is 2, and then W is just log 3. So, um, and then with 4 variables, it looks like this. One thing to point out is, oh, actually, we'll get to that in a moment. Sorry. The co-information here then is just the centermost region. For the copy bit, it's 0 because as we saw, there's some information with 2 variables, and there's an information in the third variable, but nothing that kind of involves all 3 variables. For the giant bit, it's +1. For the exclusive OR, it's that -1 in the center. And for the W, it's the -0.4 value. For 4 variables, again, it looks something like this. It's just the centermost region. But one thing to point out here is if we take the giant bit and the XOR distributions and we kind of extrapolate them to higher numbers of variables. So for the giant bit case, we have n variables that are all 0 or all 1 simultaneously. In that case, the Venn diagram has a 1 in the very center, and so the co-information is always +1. For the exclusive OR, if we extrapolate that to multiple variables, maintaining the property that the sum of the individual values has parity 0, so has an even number of 1s. What we get is that the conditional mutual informations of any 2 variables given all the others should be +1. And as we move inward, so the mutual information with 3 variables given the rest should be -1. The mutual information of 4 variables given the rest should be +1, and so on. And so in this case, for 4 variables, the XOR would have a +1 here. And so the sign of the co-information starts to lose some meaning as we allow the number of variables to change. So in the case of 4 variables, both the exclusive or the giant bit and the exclusive OR would have +1 as the co-information. And when there's an odd number of variables, they have different signs. And so just using the sign of the co-information kind of loses that meaning unless you fix the number of variables you're talking about. 1 second, please. No, go talk to mom. Go talk to mom. Sorry, my kid walked in.
Also, is it possible I see there's a few more slides. I don't want to rush. I think we should have.
Oh, I will definitely speed up. Yeah, no worries. Moving quickly, there's this other measure with the argument over the gamma. It does some weird stuff. This one I want to focus on for just a second, though. The third order connected information comes from information geometry. And so the idea here is taking kind of an Ising model approximation. What we could do for 3 variables is assume that only pairwise dependencies or interactions matter. And we can define a set of constraints on the distribution that we're interested in. So for example, this one here, we would care about the pair XY, the pair XZ, and the pair YZ. And we constrain those to match the distribution we're interested in, but we otherwise allow the distribution to vary within that space where those pairs of variables, their marginal distribution is constrained. Within that family of distributions, we then find the one with the maximum entropy. If we compare the true distribution X, Y, Z to the one where we fix each of the pairs but otherwise take the maximum entropy, the difference in entropy between those 2 distributions is known as the third order connected information. And for our 4 distributions, the exclusive OR has 1 bit and the others are all 0. That implies specifically for the W distribution here that although it exists in a situation where the mutual information of any 2 given the third is larger than the mutual information alone, implying there's conditional dependence, that is knowing 1 variable correlates the other two more strongly than they are on their own. In this case, the distribution is entirely determined by its pairwise distributions. And so there's something unusual or maybe confusing going on there, where an Ising approximation would be a perfect representation of the W distribution, but would be completely wrong in the case of the XOR. And so these two measures, the co-information negativity and the third order connected information, can give conflicting answers about what might be going on with a three variable distribution. And so let's dive into where this information diagram comes from, which will lead exactly to the dependency diagram I want to introduce. So we actually start with this Hesse diagram on the left, which is a lattice. Let's say we have no variables, or we have one variable, X, Y, or Z. We have pairs of variables, and finally we have all three variables. And the partial order here comes from whether the set of variables in one node is contained within the set, or contains the set of the ones below it. So for example, XY contains X, and it contains, or XZ contains X and Z, and so it's above those two in this lattice. And if we start looking at edges here, for example, what's the difference in entropy from H of XYZ to H of YZ? Well, it's H of X given YZ, and so we can put it in this part of the Venn diagram. If we then look at this difference here, the difference between H of XZ and H of Z, well, that's H of X given Z, which would be these two regions taken together. And so the value that we would attribute to this component down here would be G, but subtracting the L part, because L is already over here. This full moon shape would be G, and so this little chevron would be G minus L. And we can continue that with a few other edges here and end up getting that the co-information should be the sum and difference of these different conditional entropies that we get by looking at the different edges within this Hesse diagram. We can fill the whole thing out that way. And this shows that there are redundancies in the lattice that are not immediately apparent necessarily. For example, G minus L should be identical to I minus K, and those are constraints on the information within the distribution. And it allows us to take this non-planar thing and kind of embed it within a planar structure. And we're going to do the exact same thing for this lattice over here, where the nodes, instead of being represented by which subset of variables we have, instead is represented by which subset of dependencies or constraints we have. And we can build the thing up in exactly the same way. The only difference is that there's this one edge at the top that sticks out, the difference between a full three-way distribution and an Ising approximation. And that gets represented by this component that's outside of these three circles. So if we look at our four example distributions with this dependency diagram, which has taken the redundancies out of the lattice and flattened the structure into a Venn-like diagram, we find that for the copy bit, there's one bit of information in the XY dependency that's not in the XZ or YZ or XYZ dependency. It's just right there, which makes a lot of sense. We've kind of excluded the idea that Z is its own thing, and we're not talking about the independence between X, Y, and Z, but we're showing that there is a correlation between X and Y, and that's what's being picked up in this diagram. For the giant bit, we actually end up with the confusing case of a negative value. This is coming from the fact that any two pairs of variables here define the full distribution. For example, if I knew that X and Y are identical, and I knew that Y and Z are identical, then I can infer that X and Z are identical without actually having to be told that. And so what we see is that if X and Y, or if I look at X, Y alone, I have one bit. If I learn YZ, I learn a second bit, but they actually overlap. They don't tell me anything in concert, but what I do learn is that X and Z are also the same, and so we have to discount that by putting a -1 in the center. So we've kind of taken the confusing aspect of the XOR I diagram or information diagram, and now it's representing the giant bit here in this diagram. For the exclusive OR, things are very simple. we find that the only constraint or dependency that has information in it is the full XYZ distribution. And that's because any pair of variables here is entirely independent. And so as we constrain subsets, we don't actually learn anything about the structure of the distribution until we constrain the full XYZ set of variables. And finally, for the W distribution, we end up with a case that we never see in the situation of information diagrams, and that is that the chevron shapes here that are like playing the role of the conditional mutual information are the values that are negative, and the other areas are positive. And unfortunately, I do not have an interpretation for this at the moment. But that brings me to the end of the talk, I guess exactly on time. So if anyone has any questions or discussions that like to have, I'm ready for that.
Yeah, thanks so much for the talk. It's very interesting. First of all, I'd like to open the floor for any questions from the audience. I see Joe has one. Joe, you want to unmute
I was
yourself?
just clapping, but
Oh,
I can also ask a question. I'm wondering how and if Reddit is interested in information theory. Like, do they use information theory at all?
Yeah, sorry, I failed to introduce myself really. So I work on the safety ML team at Reddit. In that role, we don't use information theory very much. I used to work in data science for user safety, and in that situation, we did use various information measures to try to learn about user behavior and interactions between users. Um, Reddit as a company has no opinions about information theory, to the best of my knowledge, but when it comes to working in user safety, we are generally encouraged to use whatever methods are fruitful. And so information measures of various sorts have been very useful. Some specific ones might be the Jensen-Shannon divergence is exceedingly useful for measuring when distributions of language are similar between subreddits, for example. We also use time series information theory applied to time series to look at like entropy rates and things like that to try to identify inauthentic behavior and such. But yeah, we don't do any pure research in information theory at Reddit currently.
Cool.
fair enough. Any other questions from the audience? Okay, I have a few. So one thing or one theme that I noticed in the presentation was, okay, so first we saw for the classic Shannon entropies, there's a case of negative entropy, which arose in two cases, one for the XOR and one for the W, like the quantum case. And you mentioned that, and I agree with you, that negative information doesn't really make much intuitive sense. I was curious if you're aware of how like what approaches are used to like not just like fix the negative uh cases like by using another framework, for example, what you did to fix in the XOR case, but like directly interpreting a negative information.
So classically, I believe the negative co-information was in generally interpretation was based entirely on three variables, and the idea was a negativity was a sign of kind of synergistic effects between the variables, and a positive value is a sign of redundancy. As I pointed out, that once you extend to, let's say, four variables or something, that interpretation fails to apply. Some approaches that have been done there, probably the primary thing is if we really focus on where does this negativity come from, it comes from the situation of conditional dependence. That is, say we have variables X and Y, which have zero or a small amount of correlation or mutual information. But then once you know a third variable, they become more correlated. And the exclusive OR is kind of the prime example of that, where they are independent on their own, but once you know the value of this Z variable, which is effectively their parity, they become perfectly correlated. And the partial information decomposition approach of Williams and Beer and several others at this point kind of takes that on head on, where they take this information diagram and actually specifically they focus on one of these kind of banana-shaped regions. So the mutual information between two variables, say x and y and z, which consists of two conditional mutual informations and the co-information. And they break that into 4 components. Those components are what is redundant between x and y in discussing z. So, sorry, backing up a second, they partition the variables into 2 sets, what they call sources and targets. And the idea is z is our target and x and y are our sources. And we'd like to decompose the information shared between the target and the sources into what the sources redundantly inform about the target, what each of them uniquely determines about the target, and then what you only get synergistically about the target. Their decomposition is supposed to be non-negative, although some of the proposals for how to quantify it do involve negativity. Those are generally not well received within the community, though. But I believe their paper is known as a non-negative decomposition of mutual information. So their goal was non-negativity and interpretability into redundant, unique, and synergistic components. And in that situation, generally, the negativity is an implication that there's synergy. In fact, the co-information in their decomposition turns out to be redundancy minus synergy. And so the sign of the co-information is then related to the balance of synergy versus redundancy in the distribution. And Fernando Rojas kind of seized on that and introduced something called the O information, which is actually just the difference between the total correlation and the dual total correlation. So in that case, this value where you have this part of the Venn diagram highlighted minus this value, which in the case of 3 variables is just the co-information, but in the case of 4, 5, 6 variables is a different thing. It's basically this, but with 1 count subtracted from everywhere where there's overlap. And that is supposed to give the balance of redundancy versus synergy into higher variable sets. And so generally the sign of that O information tells you whether synergy or redundancy is the dominant factor in the distribution, but it doesn't really let you break it up and understand specific dependencies or where that synergy or redundancy is coming from. Does that kind of
Yeah, that's
a
very
dump of
interesting.
answers
No,
there?
that's great. I mean, we looked actually a bit at Williams and Beer. I think Joe might know a bit more than me. And yeah, so we're looking at kind of these 3 kind of sources of information with respect to sources and the target. But I didn't know about O information at all. It's quite interesting.
I believe he introduced it maybe 5 years ago. I can dig up that source and send it to you.
Sure, thanks. That'd be great.
All right, I will step off the stage here.
Okay. So for our next talk, it'll actually be Joseph and myself. We'll be presenting our paper, which is a feature importance method, ultra marginal feature importance, which is with causal guarantees. So Joe will start off and I'll do the second part of the talk. First, share screen. Okay, Joe, you can take it away.
Cool. Hi, everyone. So we're going to be presenting our paper, which was published in AI Stats a couple of years ago. So feature importance is quite a broad topic. And because of this broadness, it can have many motivations. So users of feature importance might want to know which features should I delete during the feature selection phase of my modeling pipeline, which features are causing changes in my response, which features are most associated with my response, which features are disproportionately altering a particular prediction, or even which features are primarily affecting my model performance. So all these different motivations can kind of be grouped based on kind of what questions they ask and their goals and motivations. So the first group is the global model feature importance. So in this framework, we want to gain an understanding of an entire model. And then the local model framework wants to gain an understanding of a particular prediction made by a model. Then the global data framework wants to gain an understanding of an entire data set, while the local data framework wants to gain an understanding of a particular observation in a data set. Now you can see here from the table that most developers of feature importance have really focused on the model group, while a very few have focused on the have been motivated by learning from data. So we're going to focus on that today. What's interesting is that while most method developers of feature importance focus on developing methods for interpreting a model, as shown in this Twitter poll by a famous feature importance researcher, most practitioners who want to use machine learning interpretability actually use it to gain insights about data. So there's a huge kind of a difference between the motivations of the developers of feature importance and the actual users. This difference is even more stark, I believe, for scientists. So in science, I like this quote from Rasher et al. In 2020. In the natural sciences, the main goals for utilizing ML are scientific understanding, inferring causal relationships from observational data, or even achieving new scientific insights. Now, this is corroborated from a bunch of different quotes from high-impact journals, yet these papers from high-impact journals use feature importance methods specifically to interpret a model rather than gain insights about data. So the first method that was actually developed specifically for scientists who want to understand and infer relationships from observational data comes from Katav et al. In 2021, published in ICML. So they developed a method called marginal contribution feature importance. They developed this method by setting out a couple axioms that they wanted to satisfy, namely the marginal contribution, elimination, and minimalism axiom. And they found that the only measure that satisfied these axioms is given by this equation 1 here. So the marginal contribution feature importance of a feature xi is given by the maximum difference between the universal predictive power, which is new here, of s and xi minus the universal predictive power of s. So this is maximized over all subsets of the feature set F. Now, in the original paper, you can kind of see the initial indications that their method is not ideal. So they ran their feature importance metric on a specific breast cancer data set, so genome-wide association study. And they found that all of their genes that they tested are given non-zero importance. So even the gray genes in this plot, which we hypothesize are not associated with breast cancer, are given non-zero importance. So that might be a problem. Further, we tested this method on a data set from hydrology and noticed 2 more downsides. So first of all, it's extremely computationally expensive. It's NP complete and requires 2 to the P model trainings, where P is the number of features. So when we ran it on a hydrology application, we had 45 features that we wanted to measure feature importance on, but due to this computationally expensive nature of this, we were only limited to 30 features. Third, we found that MCI detects very few interactions in the data, even though we'd expect in hydrology datasets everything to be interacting together. So this last point is kind of illustrated in this example here. So given a real world example, like temperature and precipitation, we might expect those two features to be spatially correlated, but we also know that they can interact together. So temperature and precipitation might give information about stream flow that isn't available from each of them individually, but can be provided by them together. So in a maybe easier to understand example, we can form the response y as being x1 plus x2 plus sine of x1 times x2 plus x3 plus x4. So this extra sine term is an interaction term. So we would expect x1 and x2 to give more information to y compared to x3 and x4. Now in the first plot, MCI correctly identifies this. So x1 and x2 are given more importance than x3 and x4. But that's in the case where x1 and x2 are independent. But if you make all the features correlated with each other, then the figure on the right shows that MCI begins to fail. And this is basically because of what Ryan was partially explaining in the previous talk, that this dependence and interaction can kind of fight against each other. So MCI isn't able to break those apart. So our objective and our main question for this work was, is it possible to develop a feature importance method that doesn't treat dependence and interactions as a trade-off? Can we detect correlated interactions? And also, can we satisfy this goal while becoming computationally efficient? So again, our goal is given a feature set F and a feature of interest xi within F, we want to find a representation of data, S, that is independent of xi while keeping as much of the original information from F as possible. And it turns out that there's this really cool connection between our goal and the goal of researchers in AI fairness. So they want to pre-process a set of features by finding a fair representation of the data that is independent of some sensitive attribute, for example, race, age, or gender, while maximizing the predictive performance. So in our paper, we use the methods of AI fairness, and there's some connections with privacy as well, to find a new preprocessed feature set, S, that obeys three kind of constraints, I guess. So first, we don't want any extra information within S. So basically, S is a function, a deterministic function of the original feature set F. S should be independent of the feature of interest. And also, we shouldn't have any information loss. So when we pre-process the feature set F into S, the mutual information between with Y should be the same. Okay, so with that, we can introduce our new feature importance method ultra marginal feature importance, which we'll denote as UMFI later on. So given a response y and a feature set f and a variable of interest xi, UMFI is defined as the universal predictive power of S and xi minus the universal predictive power of S. So within this, we assume that S is optimal given the previous three constraints that I laid out, namely that S is a function of S is independent of xi, and S was computed such that there's no information loss, basically. So this kind of leads to a very simple algorithm. So given a feature xi that we want to compute the feature importance of, we can obtain S by optimally removing dependencies on xi from f. And then we specify a method f and a corresponding evaluation function, and we estimate the predictive power of S and S plus xi, and then we just compute the difference.
All right, so to continue on, we introduced a new framework where instead of looking at all the subsets, we can just do a one-shot pre-processing to remove dependencies and then evaluate the difference over that new kind of transform set. The question now is, how do you obtain these pre-processing that are optimal in the sense that they remove the dependencies, but still preserve as much information as possible? So we have two candidates that we implemented in our paper for our evaluations. The first one's very straightforward, is through linear regression. So the idea is to take the feature of interest, so like the variable that we're trying to measure the importance of, and to use it as a predictor in linear regression on each of the other features in F. And you do this pairwise for each of these. Once you have it, then the idea is to replace each of the other features besides the feature of interest with the residual, because that will be the part that's supposedly independent. And it turns out here that when the data is represented by a multivariate Gaussian distribution, this is actually optimal according to all of our axioms. So it will actually guarantee independence completely, and it'll also preserve as much information as possible. The other pre-processing idea that we looked into was directly from the AI fairness literature by Jandro and Lum. And the idea here is to view the transformation as an optimal transport problem. So if you have some feature of interest xi, you'll again iteratively go through each xj that's not xi, and we want to transport it to some variable that's independent of the feature of interest xi, all while minimizing the information loss. So you could view this as optimal transport problem. I won't go into the derivation because that's outside the scope of our papers, including the Jandro and Lum paper, but the solution, which is in the bottom equation, is at least pairwise. The idea is to apply the conditional CDF on each of the other features. And although we didn't prove any theorems for this preprocessing method, we hypothesized that it'll be a bit more flexible than linear regression to handle, for example, discrete distributions and maybe more complicated sources of data. Okay, so now that screen might be frozen. It's not good. Okay, so now that we've explained how we preprocess, we're ready to give a few axioms that we think feature importance method in terms of explaining data should obey. The first two have to do with information theory, actually. So the first one is actually from the MCI paper by Katav. It's called the elimination axiom. I actually prefer to view it. So the elimination axiom says that if you were to remove a feature from the feature set, then the scores for all of the other remaining features will either stay the same or decrease. I prefer to think of it positively. So if you were to add a feature in, then this could only increase the scores because you're considering more information. Maybe there's some synergies that will appear only when viewing the added variable. The other axiom, okay, it's a mouthful, but it's actually quite simple. it's split into two different parts. So the elimination axiom, it tells us that when you add a variable, it can only increase. We're considering cases where you have where you would not have strict increases, where you'd actually preserve equality. And this happens when you add redundant information. So what does that mean? It means you're adding a function of the variables that are already in the feature set F. In this case, the invariance under redundant information part tells us that for each pre-existing feature, its scores will be unaffected by the introduction of some redundant variable. The symmetry under duplication is a subset of that. So it's if you literally just add a duplicate feature, then the duplicate and the original will have the same feature importance scores. So we have two information theory axioms here. Our other axiom is a blood relation axiom. We think this is pretty neat axiom. This is causality informed. So the idea is that if you have a full causal graph, like including all of the unobserved, or including all the confounders, I should say, then the only features that should be given a non-zero importance with respect to the response y are the ones that are blood related to y. So what that means is either a descendant of y, like x4 is in this graph, or it shares a common ancestor, or literally is an ancestor. And all of the other ones, in this case x1 and x2, would have zero importance. We think this would be a desirable property. And we actually prove that our three axioms, the two information theory-based axioms and our causality-based axiom, are satisfied under ideal conditions. So we kind of have two parts here. This part I mentioned before. It's that if you use linear regression in a multivariate Gaussian setting, then this is an optimal way of removing dependencies. And then if you have a multivariate Gaussian and you also suppose that the full causal, like you assume some faithfulness condition on the full causal graph, including all the confounders, then you would also solve the blood relation axiom. So all three axioms would be proven. So now that we have some theoretical guarantees, I'll quickly go into some of the experiments. The first thing we want to check is, so this was the experiment that Joe already showed. We want to check that the same experiment that MCI worked on in detecting the extra interaction term still works for UMFI when we do the removal of dependencies part. And we see that this indeed works. So here, x1, x2, x3, x4 are all independently distributed. Now we return to the correlated interaction experiment. This is the main one that we want to see a difference, because MCI actually failed to show that x1 and x2 from the same response, like the exact same response with the extra interaction term. We'll now see here that our method, once you remove dependencies, is able to resolve that previous tension. And it's able to show that xi, x1, and x2 actually do have more importance than x3 and x4. So the preprocessing in both cases by linear regression and optimal transport do the job. We also consider a correlation experiment. So this is one that MCI succeeded on as well. In this case, we can see that the response depends directly on x1 and x2. x4 is not integrated at all, so we should expect it to have basically zero importance. But x3 is virtually identical to x2. So basically the first three variables should have high importance. The last one should have zero. And all three methods do quite well. But one thing we do note is that MCI still, as we pointed out, gives some honestly significant importance to a variable that should not have any importance. So that's one slight downside. And our last simulated data experiment, we test out the blood relation axiom. And so we look at a causal graph, the same one from before, and we generate data correspondingly. Here, S is unobserved. So you'll see it's not one of the features. But despite that, even though it is an unobserved confounder, the blood relation axiom is at least experimentally satisfied in this case. So we see that the non-blood related features, x1 and x2, are given zero importance by our method. All this is not true at all for MCI. And we see positive importance for x3 and x4, which indeed are blood related. And we also actually see X4 is closer to Y, so this might explain why it has more importance than X3, which is connected only through S. We also have we also replicated the experiment on real data, the BRCA gene association experiment. The one thing we changed though was just to be completely sure that these 40 other genes really have no association with breast cancer, we randomly permuted them just to break any existing association, if at all. And we see here that once again, the problem with MCI was that even though it ranked the top 10 properly, it's not as interpretable because the other 40 genes still have quite high significance. Whereas for our methods, because of the blood relation axiom, it guarantees zero importance. So it's much more interpretable. You can just take the genes here that are given non-zero importance, say these are the ones that we care about. We also pointed out that MCI has to optimize over all possible subsets, so it requires 2 to the P model trainings. Ours is just linear because it's a one-shot thing where we pre-process and then that's it. You don't have to do any kind of search. And indeed, we see here that for both of our pre-processing methods, we can process way more features for the same time budget. So yeah, MCI really struggles, and we can process thousands of features in the time that it can maybe only process 100. So in conclusion, what we've shown, so first of all, we think that MCI was actually a very good work because it was the first method that we're aware of that made a concerted effort to learn from data through interpretive feature importance. And we actually like their idea of kind of the marginal importance. But the problem was that, okay, for one, you have to search through all subsets, so it's not very computationally feasible for large data sets. But more importantly, we'd say is that this clash between dependence and interaction will cause undesirable effects. And we also see that because it doesn't have certain causal guarantees, it'll give positive importance to things that should be actually given zero importance. Just by incorporating dependency removal into the framework, we're able to solve all of these things. We have a one-shot algorithm that's much faster, and more importantly, it has data guarantees for both the blood relation axiom and for correlated interactions. For future work, we think that'd be worthwhile to explore other ways to remove dependencies. For example, using more sophisticated ways with optimal transport to get rid of higher level dependencies besides pairwise. Also, principal inertial components and neural networks. And finally, we also want to see how faithfulness changes if we modify the variables with this kind of transformation. Thank you for your time. And yeah, now can take any questions that anyone has.
I have a quick question. So pardon if I misunderstood, but this work was all about the global data setup that was discussed initially, right?
Yeah.
Is there any or have you explored extrapolating this or anything to the local model or local data situation? Because at least within within my area, the local is often very important to understand why an individual decision was made by a model based on either the data or the model itself. And this approach feels very strong and we currently use SHAP for this kind of use case, but I feel like this is perhaps much stronger in that sense. So is there some exploration to the local framework for this kind of work?
Joe, do you want to take it or do you want me to take it?
Yeah, I mean, as of now, there's literally nothing for the local data example. I mean, this graph or this table was taken from a paper in like 2023. So there's nothing for local data at the moment, but we are really interested in doing that eventually. I think I had some ideas of how to do it like a year ago, but yeah, if yeah, if you're interested, definitely contact us and we can discuss.
Yeah, will do. Thank you.
Any other quick questions before we move on to the third talk?
So you kind of mentioned that the way you go about doing this is you have the data set, the reduced data set that you construct. Is it always possible to be able to satisfy the three axioms that you had for constructing that S data set? Because
Yeah,
it feels,
that-
yeah.
that's a tough.
Yeah, constructing that S data set is definitely the hardest part.
Mhm.
I mean, we find that optimal transport does a pretty good job, and it works really, really well on the gene data set.
Mhm.
But we also tried it on a hydrology data set. It worked kind of, but less well and definitely not optimally. So
I see.
we found that there was still some dependence on xi. So the second axiom here wasn't quite satisfied. But yeah, that's why we feel that looking into further pre-processing methods like neural networks and stuff might be a really interesting avenue for future research.
Yeah, as for mathematical proofs, I think the only thing was, yes, in a kind of toy example, when we have multivariate Gaussian, we use linear regression. I don't believe we proved optimality in any other case, but in experiments, yeah, it worked all right, except for the one that Joe mentioned with more complicated interacting climate data. Okay. So now
Well, I think technically optimal transport should be optimal, but it's just estimating that conditional CDF is really hard in practice. So it's kind of
I don't know about the
not perfect.
part. I don't know. There's some weird stuff, but I don't know. Can look into it. I'd like to now introduce the third talk by Dr. Praveen Venkatesh from the University of Washington, and he'll be discussing quantifying information flow and information interaction in neural circuits. And oh yeah, I'll stop sharing.
Yeah, so thank you so much to the organizers for inviting me, and thank you all for being here. Oops. So let me know. I got notification that my internet might be a little bit unstable, so let me know if you are having difficulty in any form. You have to stop me, and I'll see if I can do something about it. But let's see. So yeah, I actually set up the talk to talk because this is about this is a workshop about causality and information theory. I was actually trying to focus a little bit more on the information flow aspect of some of my work, but I realized from the previous two talks that perhaps the interaction bit might be more interesting. And so I'll see if I can keep maybe a bit more time towards the end to talk about this, but we'll see if we go on. So yeah, I'm a scientist and Shanghai Foundation Fellow at the Allen Institute, which is predominantly an institute that works at neuroscience. And I have been interested for many years in thinking about applying ideas from information theory to neuroscience. And I think the idea of information flow, thinking about information flow, really came up in that context. So let me talk about some of the work that I've done here and how it connects to causality. So the main motivation for some of this work was the neuroscientific one, as I said, where neuroscientists are often interested in understanding how the brain works, broadly speaking, but more specifically, how it is that different brain regions come together to actually solve a task. So in some cases, they're also interested in understanding how certain pathologies may arise, which regions of the brain are maybe responsible for these kinds of pathologies, and how the information flows inside of these networks actually give rise to pathologies. So for instance, if you wanted to study addiction, for instance, you might consider the network in the brain that's called the reward network, which consists of a bunch of interacting regions. And from a static picture like this, which comes from anatomy, what they would like to do, what neuroscientists would like to do is construct a dynamic picture of how information is actually processed by this circuit. And so you might say that there's a mouse that's maybe performing some kind of task, an addicted mouse that's performing some kind of task. And at different points in time in the task, there's going to be different kinds of information flows between these different brain regions. So there might be information flows between a certain set of regions at the start of the task. Then when some cue is presented to the mouse, then the mouse takes some kind of action. Finally, when the mouse receives some kind of reward, at each of these different points in time, there are different pieces of information that are flowing between these different regions. And this changes as a function of time. And that's what neuroscientists would like to be able to track to understand how the system works. And eventually the goal, of course, is to be able to go and intervene inside of these circuits to either test causal claims and to understand which regions are actually causally relevant for this, so that you can maybe design drugs to treat addiction and so on. So for the purpose of understanding information flows, our takeaways over here were that you want the information, you want to be able to track information that is often about something. So in each of these cases, the information was about a stimulus that the animal received, information about the value of these different stimuli, information about the choice that the animal makes, perhaps. So those are the pieces of information that the information is about something, that's what you want to be able to track. Secondly, the fact that the information is dynamically changing over time, and you want to be able to track how it changes as a function of time. And thirdly, that you really want to track how it flows within the network, so that you can understand where you can intervene at different points in time. So that's the eventual goal of any framework that should seek to study information flows and give an understanding of information flows of the kind that neuroscientists might be interested in. So with that setup in mind, we kind of came up with a computational model of the brain that could help us define information flow in a concrete manner. And so here it was set up to try and reflect as closely as possible the picture that I showed you before, where you have a bunch of brain regions that are interacting with each other. There could be some feedback between these different brain regions. And what we're interested in is how information about some stimulus that comes into one of these regions actually flows as a function of time. And so corresponding to that, we said, let's have a bunch of computational nodes that reflect the processing that is performed by different brain regions. And then let's, in order to kind of deal with this possibility of feedback communication, let's time unroll this graph. And so you have the same three nodes that are now indexed by time, but anything that they process and any piece of information that they send out is going to be sent out forwards in time. And so by time unrolling, we're able to deal with feedback. And then what I'm going to do is I'm going to assume that the transmissions that these computational nodes that they're sending out, we're actually able to measure these transmissions. So here, when I say x of E0, I mean the transmission on some edge at some point in time. That's what that means. And what I'm assuming here again, once again, is that these nodes are really not random variables. Random variables are the things that are sitting on the edges, the transmissions that you're measuring. The nodes are really just functions that relate these transmissions to one another. And so these nodes represent some kind of stochastic function of each of the input transmissions that are coming in, and you could have different stochastic functions of these framework, which hopefully represents something about different brain regions that are communicating with each other. Is you have some message or some stimulus that comes into this framework at some point in time, and you'd like to understand how information about this message flows through the whole circuit, and then eventually becomes some kind of response that the animal could make. So what I'm going to, the kind of pieces of notation that you need to care about here are the fact that I'm going to use the letter M to refer to the message, which you can think of as being a stimulus, for instance, but it could be many other things. It could be a response that the animal makes also. And X of ET really just refers to the transmission that is indexed by a particular edge at a particular time. All right. And the goal is here to actually track it. All right. So what's a suitable definition of information flow? Well, because we have access to the message that we're interested in, and we have access to all of the edges, the transmissions on these edges, one of the most obvious things that we could come up with was, why not define mutual information, define information flow just using mutual information. So you say that a particular edge has information flow about the message if you see that there's dependence between the transmission on that particular edge and the message that is of interest to you. So the reason that this kind of a definition doesn't really do the job is that there are examples of the kind that have come up in the previous couple of talks, which relate to XORs. And essentially the idea here is you could have the message M. So let's say that you're trying to communicate the message M from the node A to the node B. But the way you do this is that in the middle, you actually combine it with some independent noise Z, and this is a noise variable that is generated within the brain. And so now if you do that, and in this case, I'm going to assume that these are all Bernoulli half, and that I'm going to use XORs to corrupt the random variable M with noise. So if I do this, then actually what you can see is that you are no longer able to track how the information flows inside of the system. So what I'm going to do in the meantime is I'm going to kind of preserve the variable that I'm using to corrupt the Z. I'm going to keep it as an independent, along an independent path. I'm going to retain that variable, and then at node B2, I can actually subtract out the value of Z to recover the value of M. So if I set things up in this way, then at this particular point in time, I find that, and as a result, if you try to track how the information about M flows through the system, there's a point in time where you actually lose track of the information, which kind of defeats our intuition of what we would like for it to be able to come up with a definition that's able to actually track the flow from the input to the output. Am I still coming through okay?
It's a little bit choppy for me, but I mean, maybe like every 10, 15 seconds on my end.
Is it still understandable, or is it
yeah, it's understandable. You might want to just turn off your video. Sometimes that helps a bit.
That's a great idea. Okay.
Yeah, I'll turn off mine too, just in case.
Okay, perfect. So let me know if it becomes choppy again, and I can try connecting using a different device or something like that. And I should be okay on time. All right. So the idea here, right? So we wanted to be able to come up with a definition of information flow that is able to capture the fact that you have information about the message that still exists within this network, but it now is not expressed, is not now represented in a single edge. Rather, it has this distributed representation where it's represented amongst multiple edges. And really, this is the concept of synergy that Ryan had alluded to in his talk. And this is something that I'll try to come back to at a later point in time in my talk as well. And so how do you deal with the fact that there's another edge C that really is helping you recover the value of M here? Well, you could try to use a different definition which actually accounts for that other edge that could help you in some way. And so we look at the conditional mutual information based definition. And so here I will allow you to condition on some other edges, ET prime, and I'll allow you to condition on the transmissions of those edges, and then I'll see if this fixes the problem, right? And so in this case, I would naturally condition on the other random variable C when I'm trying to look for information flow on this particular edge. And this really does resolve the problem, because by conditioning on Z, I can reveal the dependence between M and M XOR C. So in general, if I just looked at M and M XOR C by themselves, they look pretty independent of each other. But the moment I tell you the value of C, you might notice that whenever C is equal to 1, and M XOR C are actually not equal, in the sense in which giving me the value of C or conditioning on it really reveals the dependence between M and M XOR C. And so this is one way in which you could try to resolve this idea that I need to be able to condition on other edges in order to detect the presence of information and be able to consistently track the flow of information within this kind of network. All right, so in general, if you actually had to make a formal definition out of this, it turns out that you have to condition not on just individual other edges, but rather on subsets of edges. And this is where maybe ideas like ultra-marginal feature importance or the ideas behind that could actually become useful, maybe computing these kinds of quantities, which is you have to actually search over all subsets. And that ends up being a problem computationally, but it is important for the definition itself. And that's because while in this particular example, you only need to condition on one other edge, in general, there might be situations where you need to condition on more than one other edge, or condition on some edges, but not other edges. And so it becomes important to actually have, for the purposes of this definition, conditioning on a subset of edges. So given this, you can actually show that if you take a definition like this, where you say, I'll allow you to condition on a bunch of other edges, and then I'll look at whether the edge of interest carries mutual information about the message. This ends up being a really good definition of information flow about this message. And the reason for that is you can actually prove a theorem about it. You can show that if the message M comes into the network at some point in time, and then there's some function or some response that depends on this message that's computed at a later point in time, you can guarantee that there will be an information path that leads all the way from the input of this network to the output of this network. You can guarantee that there must exist some information path. And so you can kind of prove a theorem which I can formalize that looks like this. So that's really great, and so that makes this a pretty nice definition. But it still has certain problems, and I'll get into this. And this is where the idea of causality really comes in, and trying to understand things from a causal perspective really help here. So this has to do with what I call information orphans. So I really kind of cheated when I showed you some of the pictures earlier, which is I kind of omitted one particular thing, which is when I look at this particular picture and I say that using the definition that I showed, this particular edge has information flow. It's also true that this edge has information flow about the message. And that's because if you look at the conditional mutual information M and MXRC given C, that's greater than 0, but it's equally true that the conditional mutual information M and C given MXRC is greater than 0. And so what ends up happening is that you actually see information flow coming out of a particular edge, out of a particular node, while these edges don't really have information flow, and so there's no information flow going into the node. So this is really counterintuitive. You get this, what I call an information orphan, in the sense that there's no information coming in, but there is information going out. And so this is really undesirable for a couple of reasons. The first being that there's no conservation of information flow, right? And the second being that this node, or rather this transmission Z, which was really never computed from the message M and doesn't depend on the message M in any particular sense, it is considered to have information flow in this context. And so that's another undesirable thing. So one of the kind of ways we thought about to try and fix this was to maybe use some kind of a pruning method. So you go backwards from the output all the way to the input, and you try to prune out the edges that lead. We hypothesized that maybe what this could do was to try and recover. So by pruning, you're able to guarantee that you have conservation of information flow. And hopefully, you're also able to get rid of these edges that transmit Z. So maybe you're able to get rid of the information, the edges that carry no information about the message in some sense. And so if we kind of want to see how this might happen, right? You might have a complex information graph that you're able to compute. So these are the set of all information flows, and you can just use a depth first search to go backwards in time and then see, oh, okay, this goes maybe to an orphan, so I'll eliminate this. Then take another path that goes all the way back to the input. This one goes back to the input, so I'll preserve it. And likewise, there might be multiple paths that go to the input. There might be multiple orphans, and you can get rid of all of these. So this is a valid way of doing things and making sure that you are able to get rid of these orphans. But unfortunately, even this kind of a pruning algorithm does not always remove random variables like Z. And so this is a really, what I'm going to present next is a sort of weird and pathological counterexample that presents a case in which you're not able to remove Z using pruning. And it looks something like this. So I will explain what's going on here. So here you have the message M, and just as before, you are going to combine it with another random variable Z, produce M XOR C, and then eventually subtract out the value of Z to recover the value of M. But what I'm also going to do is that somewhere in the middle, I'm going to have is a point in time where I preserve M XOR C and I preserve M and Z. So I kind of vectorize them. I just keep them next to each other. I transmit both of them before jettisoning M to just keep the value of Z. So what I've done here is I've created a setup where at a particular point in time, you have M XOR C and then the vector M and Z. And if I now look at the definition of information flow, where I try to condition on other edges at that point in time and ask if I'm able to see mutual information here, the problem is that I actually don't see mutual information, even conditionally, on this particular edge. There's no information on this edge, but there is information flow on these. So you still have your information path, it contains Z, and the edge that had M XOR C becomes the orphan. So this is like a really weird counterexample where this happens. And And it's useful to maybe think about why it is that we have this intuition that Z is the thing that wasn't computed from M. And so we have this intuition that this is not the correct path, that this is the correct path. And so it really is helpful to kind of go back and think where that intuition really comes from. And maybe introspect into why Z even carries information flow based on this definition. And the reason for that really is quite fundamental. So if you look at, let's say that I call MX or Z, I just label it Y, and I look at the joint distribution between M, Y, and Z. So if I do that, it turns out that this joint distribution is actually symmetrical in Y and Z. And so, and because of that, what that means is if I didn't know, if I was just getting data out of this entire graph, right? So I'm measuring a bunch of brain regions that are emitting some data, and I'm trying to actually look at the joint distribution of the activity of all of these regions, then what I kind of see is that I won't be able to distinguish which one of these variables actually looks like MX or Z and which one of these looks like Z. It could equivalently have been, this is a random variable Y, which is noise, and this is MX or Y, right? And so this makes it impossible to actually distinguish using a joint distribution between these two random variables. And that's the reason why both of them necessarily end up having information flow based on the kinds of definitions that we're able to come up with. And so it's really any observational definition of information flow, which is a definition that's based on a joint distribution, will have to face this issue. And the only way to actually distinguish these two is to go beyond the joint distribution, which is exactly what you're able to do if you kind of think about a causal framework. And so that's one of the things that we try to do. We try to say, let's think about how, if you insert the idea of causality into this kind of a framework, does that fix some of the problems? And to what extent can you actually use this in order to inform the way in which you go about constructing a definition of information flow? So I'm sure that people here are familiar with this idea, but I'm going to kind of describe it anyway. So the idea of counterfactual causal influence, or the idea of counterfactuals, generally speaking, is to think about what would have happened if the variable M had taken a different value. And more precisely, for a particular realization of all of the random variables inside of your system, what would have happened to the downstream variables in your system if M had taken a different value while keeping all of the other sources of randomness fixed, right? And so in this case, the way to think about this is, let's say I have this graph once again, and I now have M a particular value, Z taking a particular value. But now I change the value of M while keeping the value of Z fixed. So if I do that, that now changes the value of M, it changes the value of MX or Z and changes the value of M, but it crucially doesn't change the value of Z here. And so this really is the thing that captures our intuition of when we say, oh, here MX or Z depends on M, but Z does not depend on M. It was never computed from M. So it's really counterfactual causal influence as a theoretical construct that captures this intuition, while observational definitions aren't able to capture the same intuition. So if we use this as a notion of information flow, you can kind of formally define. So as I said, this now differentiates between MX or Z and Z. And if you can now use counterfactual causal influence as a measure of information flow, and you can say that a particular edge carries information flow if it's counterfactually causally influenced by M. And that happens when there exists some pair M and M prime along with a fixed realization of all of the other random variables W, such that if I keep W fixed and I change the value of M, then the value of that edge, the distribution of the random variable changes. And that's the sense in which a particular variable could be counterfactually, or a particular edge, sorry, could be counterfactually influenced by a change in M. So using this kind of a definition of information flow, you can now kind of see that in this graph, you kind of recover the correct path. You don't have any orphans. And similarly, in the more pathological example, you can show that you recover the correct path. You don't recover the one with Z. And in fact, you can also show that this definition of counterfactual causal influence, it satisfies the property that you don't have any orphans, so you're able to get rid of that. And it satisfies the property that you have information flow. You're able to guarantee that you can get an information path that leads all the way from your input to your output. Unfortunately, of course, counterfactual causal influence is a theoretical idea. It's a theoretical construct. It's not something that you can actually evaluate in practice because it requires you to keep these internally generated random noise variables fixed. So if you had some noise, so Z here was an internally generated variable in the brain, how can you change the value of the stimulus while keeping the internal noise within the brain fixed? That's not an experiment that you can actually conduct. And so this is not something that you can evaluate in practice most often. And that becomes a problem, just in terms of taking this idea to practice. But it can serve as a kind of a North Star or the holy grail of what information flow should really represent. And it's something that you can measure other information flow definitions against. And so one thing that you can try to see is how does RM information flow definition, how does that compare against counterfactual causal influence? And you can kind of see that information flow guarantees information paths, much as CCI does. Information flow doesn't have orphans once you've done some pruning. And maybe in many cases that are not those contrived counterexamples, you're able to capture these intuitively correct edges even with information flow. But that's something that we need to kind of think about more theoretically. But of course, the critical thing is that this kind of a definition is actually usable in practice. Maybe it's a little bit hard to compute, but it's actually something that you can use in practice. Whereas this is just a theoretical quantity which you can't actually compute. But it's helpful to think about what kinds of definitions you come up. So with that, I come to the end of the information flow section of the talk, and I will pause for questions in maybe a minute. But because this is also had to do this, the workshop had to do with thinking about understanding these kinds of ideas from data. Let me just take maybe 1 or 2 minutes to talk about a couple of contributions that I've made much more recently in the field of measuring information interaction. And this really goes back to the idea of, so, right, as I mentioned, you could have a situation where X and Y contain information synergistically, and you might also have different situations where you actually want to measure whether in neuroscience, whether X and Y have a redundant information about the stimulus. Do they actually contain the same information, or does X maybe have some unique information that Y doesn't have access to? And this is really the idea of partial information decomposition that Ryan talked about. And similarly, the context of fairness in artificial intelligence is again articulated in the previous talk. You might have a situation where you want to understand the contributions of different features to bias. And so each of these things, in each of these cases, it's useful to maybe think about quantities like unique and redundant pieces of information. And all I want to say in the last minute is that, so I'm not going to actually introduce the partial information decomposition because there's not enough time. But the idea is what we were able to do was we were able to come up with ways of quantifying these measures, unique, redundant, and synergistic information for Gaussian random variables. And I'm just going to skip ahead here. What we were able to do was we were able to say, so as I said, I'm not kind of talking about the definitions themselves, but we were able to compute these very efficiently for Gaussian random variables by making some assumptions that all of these were jointly Gaussian random variables. And when we did that, we were actually able to kind of decrease the complexity of the optimization problems that are necessary for exponentially, and by doing descent methods to actually solve these. And we have some code that's available to do this. And I'll just mention that we were able to validate this against ground truth examples and show that it can correct with bias. And we were also able to use this in practice to actually measure the redundancy between different brain regions. And sort of kind of summarize that in a second. The main takeaway that we kind of got was that if you measure the redundancy between different brain regions as a function of time, we found that at specific points in time when the animal needed to make a response, we found greater redundancy between the brain regions compared to points in time when the animal did not need to make a response. And we kind of hypothesized that what might be happening there is that the information, because the animal needed to make a response based on the stimulus had to be encoded more robustly, corresponding to an increased redundancy between different brain regions. And so that's kind of what we hypothesized was going on there. So with that, I'll kind of conclude my talk saying that this is part of a larger research vision of mine, which has to do with understanding how information is represented in the brain as well as in artificial neural networks, how information is communicated within these kinds of circuits, and then some work that I've done in neuroengineering to actually detect and then maybe influence how information is communicated and represented within the brain. So yeah, with that, I'll conclude and happy to take any questions and maybe a bit more about the representation aspect if that's something that you're interested in.
Thank you for a wonderful talk. Are there any questions from the audience? If not, I have one, but I just want to see first.
Yeah, real quick. What was the CCI measure?
Yes.
Feels like a really robust method here for well, if you can do these kind of things. I've seen one paper before that does something vaguely similar. I think it was by Nihat I and Daniel Poloni. They did some kind of like interventional mutual information based on Pearl's causal calculus stuff. I wonder how similar the definitions here are and if there's any relationship. Yeah, I can dig up that reference and send it to you.
Yeah, I think that. So I right. No, I think I'm familiar with the one that you were talking about. Is this the one by Nihat I, or is this the one by? Uh,
Yeah, that is the one I'm thinking of.
it might be right. So I think that so I think there's a lot of confusion about
Praveen, you're a bit choppy now.
measures and I think that one of the things that's very unique about the way information flow adoption that was happening. So is that we always considered information being about the random variable m, and so it's always information flow about a particular message. This was actually something that I feel other definitions of information flow didn't quite capture. It ended up being more often than not something more Granger causal, right? So you say that, or something similar to transfer entropy of directed information, where you say that I have two nodes, I have a bunch of nodes in the system. I don't know which nodes are talking to which other nodes. And so I'll use time series information to infer the edges in this graph and ask, is node A talking to node B? And we want to go beyond that, right? We were asking not just, in fact, we assume that we know that node A is talking to node B, but we want to know, is the communication that node A is sending to node B, does that actually depend on a particular message or not? And so we were thinking about maybe something that's second order compared to the other classical notions of information flow. And I think I might be wrong about this, but I think that the measure that Nihat proposed is a great measure. Actually, it's a more graphical way of thinking about information flow. And you're right, it does have some basis in causality. But if I remember correctly, it didn't capture quite the same idea or the notion of whether there's a particular piece of information that's actually flowing through the network. But yeah, it's been a while, and I need to kind of go back and think about the differences between his work and mine as well. Yeah, great question.
Thank you.
I'd like to thank Dr. Venkatesh again for a wonderful talk. Because we're running kind of short. I think one thing we could do, if people have additional questions, maybe jot them down. And tomorrow we should have extra time because we won't have a full line of speakers. So that could be a good opportunity for just more discussion. But because we're running a little short on time, now I'd like to introduce our last speaker of today's session, Dr. Raha Marafa, to present causal feature selection in the era of big data.
Alrighty. Hi, everyone. It's a pleasure to be here, and I would like to thank the organizers for inviting me. My name is Raham Arafa, and I'm an assistant professor at WPI. So the theme of my talk is going to be a bit different from the previous presentations. In this talk, I am going to actually explain to you. I'm going to actually take more like of a data-driven approach and see how we can actually use causal feature selection in the era of big data, in which it's filled with like data-driven machine learning and neural network algorithms. In particular, actually, I am going to explain how we can use causal feature selection to make machine learning algorithms more responsible. So with this, let's start the talk. And I am actually going to first introduce the concept of machine learning in the era of big data and what is responsible machine learning. Then I'm going to explain to you the concept of feature selection and causal feature selection and what's the role of causal feature selection in responsible machine learning. Then I am going to explain our recent work on how we can use causal feature selection to make machine learning models, in particular large language models, more interpretable. And with this, I will conclude my talk and I will be ready to take any questions. All right, so we are in the era of big data in which plethora of data is available and it's very easy to access. So that makes huge advances in machine learning. Actually, we've seen before that with the creation of ImageNet data set, which is a big data set, there comes the advances in computer vision, neural networks, and with the recent access, to the internet data and Wikipedia and all these like big data that made it possible for us to have this huge advance in natural language processing, which is the advances in the series of GPT, ChatGPT, GPT-4, and etc. But here's the thing, when we have like this kind of training mechanisms, even though they make decision making like a piece of cake, just because there is no human supervision in the training objective, and whatever we train these models is pure based on statistical relationships and statistical objectives. These machine learning frameworks often face failure modes. For example, if we visualize the internal of the machine learning models, you can, like a machine learning image classification model, you can see that the model oftentimes, instead of focusing on the main object for the classification, it's going to focus on the background, which is a huge failure case. Or you can, if you take like the example of machine learning recommender systems, you can often see that, for example, for the case of job application, it's going to recommend the men's job application more often. That's only because the training data mostly involves male applicants rather than female applicants, and that makes the decision of the machine learning frameworks unfair. Or you could see that there are many instances that shows that if you slightly perturb the input data that you have, that will result in a misclassification of the decision of the model. So these are huge failure modes that makes it very difficult for us to trust the decision of machine learning models and deploy them in the real world scenarios. So there it comes, as a response to this, there comes the field of responsible machine learning. Basically, the responsible machine learning field focuses on four main aspects. The first one is going to be interpretability. Basically, this focuses on developing algorithms to understand the black box machine learning models. The second aspect is going to be fairness. So basically, the goal here is to develop machine learning algorithms that do not discriminate based on protected attributes, let's say the gender, the race, and etc. The third aspect is robustness. So basically, the goal of this aspect is to develop machine learning algorithms that are robust to adversarial perturbations. And then the last one is generalization. So basically, the goal here is to have machine learning frameworks that can be deployed in any environment, and then they can generalize to unseen environments. So what is the role of features in responsible machine learning? At the end of the day, these machine learning frameworks are essentially extracting features and patterns from the data and use those features to do decision making. So if we can come up with a framework to understand these features that are used to make decisions by machine learning models, then that means we're good to go and we can actually do something to make our machine learning frameworks more responsible. Let me give you some examples with respect to the four aspects of responsible machine learning field. The first one was interpretability. So the goal here was to make the decision, to interpret and explain the decision of the machine learning frameworks. So if we can understand which features have caused the model's decisions, that actually contributes significantly to the explainability of the model. Or in the field of fairness, if we can understand the causal relationships between the features, then that actually helps us understand. So what are the features? What are the causal effect of the protected attributes on the rest of the features, and what kind of features we can safely remove from the classification? So we basically make the effect of the protected attributes on the final decision 0. Or in the field of generalization, it's well known that if you take up all the causal features and build your machine learning model on the causal features, then the final classifier is going to be invariant across different domains. And finally, in the field of robustness, it's been shown that if the spurious features learned by the models are the main reason behind the adversarial vulnerability of the models. So this all tells us that we need to go all the way back and try to understand the features of the model. And if you look at the theme of all these examples I gave you, you can see that we are not looking only for any features. We are actually looking for the features that have some sort of causal impact on the final outcome. All right, so this takes us back to one of the fundamental concepts in the field of machine learning and data mining, which is called the feature selection. So I will give you an introduction of feature selection in case some of you are not really familiar with it. So feature selection is basically the process of selecting a subset of relevant features to build the predictive model for a given target or class variable. So the goal of feature selection essentially is to eliminate the irrelevant or redundant features. So basically when this field was built, the main reason was that if you take up all these irrelevant and redundant features in your classification, then that will result in overfitting and degradation of the performance. So the main goal of feature selection was to only select a subset of features that were relevant for the prediction of the final outcome, and build the model built upon that so that the model is simplified and that does not result in the overfitting. So the objective of the traditional feature selection is very simple. Basically, it tries to find a subset of feature S that minimizes the loss of the prediction. As you can see from this objective, there is no causal relationship involved, and this is purely based on minimizing some statistical correlations. However, as we discussed before, what we'd really need, if you really want to build up the trust between humans and machines, we need to take a look at causal features. And what we really need is going to be causal feature selection. So before we actually talk about the causal feature selection, let me give you an example of feature selection and its output. So let's assume that you would like to build a model that predicts the lung cancer from historical patient data. And the data includes these variables: peer pressure, anxiety, yellow fingers, smoking, attention disorder, genetics, car accident, fatigue, coughing, and allergy. So if we use traditional feature selection based on the objective we saw in the previous slide, it might choose, depending on the correlation between these variables and the final outcome and the data that we've used to do this kind of analysis, these set of features might come up: yellow fingers, anxiety, genetics, fatigue, and peer pressure and coughing. So we can see, probably from that particular data that we analyzed, these features were highly correlated with the final outcome. However, if you consult with a medical expert, they immediately tell you that yellow finger is not a cause of lung cancer. That rather it's like a side effect of smoking, which was another feature that we had in our feature set and could be potentially the main cause of lung cancer. So this shows that directly optimizing that statistical objective based on analyzing the correlation is not really gonna give us the causal features that we are looking for. That means we need a new field called the causal feature selection, which actually has recently attracted a lot of attention from the machine learning community. So the goal here for the causal feature selection is to identify a set of features that have causal relationships with the final outcome rather than purely relying on the statistical correlations. And the way it goes is that all the causal feature selection algorithms aim to identify the Markov boundary or a subset of Markov boundary. For example, the set of parents and children of the class variable, and include that in their analysis. So this Markov boundary usually actually is only defined in the context of Bayesian network. And it can be shown that if the data generating process is faithfully represented by the Bayesian network, this Markov boundary is actually unique for every class variable. And it consists of the parents, children, and spouses of the class variable. So let me demonstrate the concept of Markov boundary to you using the causal graph or the causal Bayesian network of the data. So basically we said that if the data generating process is faithfully represented by this causal Bayesian network that you can see on the right, then the concept of the Markov boundary of the outcome variable, which here in our causal graph is denoted with Y, consists of set of its parents, children, and the spouses. And as you can see, these are the highly relevant features that can be used for the final classification, whereas in this causal Bayesian network that represents the data generating process, we also have irrelevant features like X10 and X11 that do not have any sort of relationship with the final outcome, as well as redundant or spurious features such as X4, X7, and X9 that are weakly relevant with the final outcome, but they do not have the direct causal relationship, and therefore they do not belong to the Markov boundary of the final outcome. So let's go back to the previous example that we had, the example of prediction of the lung cancer from the set of variables. If we formulate our data generating process in terms of this causal Bayesian network, you can see the corresponding Bayesian network in this slide. So now analyzing this causal Bayesian network and the Markov boundary of the lung cancer, we can see that the variables smoking, genetics, allergy, coughing, and fatigue are the only variables that belong to the Markov boundary of lung cancer. And all the other variables should not really be taken into account when you're doing your prediction. And that actually rules out that yellow finger feature that we saw would come up as one of the highly predictive features and would be selected as one of the features if we perform the traditional feature selection. All right, so now let me give you an example of how we can use causal feature selection for one of the most important concepts, an aspect of responsible machine learning, which is interpretability. So as we discussed before, machine learning models are black boxes. That means that we have no idea how they make, especially when it comes to deep neural networks and these days transformers, we have no idea how they make their decisions. It's completely black box. So it makes it very difficult for us as end users to trust their decisions. So in the field of interpretable machine learning, we aim to improve the ability of humans to understand how this decision is made and why ML models produce these results. We have different types of interpretability. We have example-based interpretability, which is more corresponds to the local interpretability that was discussed in the previous presentation. And we have model-based interpretability, which is more like global interpretability. So in the for the example-based interpretability, one of the most important approaches that is very understandable and acceptable by especially the practitioners is counterfactual explanation. So, which is going to be the focus of this talk, and I am actually going to explain to you how we can leverage causal feature selection to generate faithful counterfactual explanations for large language models. But before that, let me take a moment to explain what are counterfactual explanations. So in general, in terms of causality, when we talk about counterfactuals, they are designed to answer hypothetical questions from the data. And these questions always involve like hypothetical scenarios, like, for example, what would have happened to the Y, the final outcome of the model, had I not done the X, or had I had like a different feature? When it comes to counterfactual explanation, we actually leverage pretty much the same concept to answer why and how questions about the decision of the model. So pretty much the questions we are trying to answer in this context is going to be why the model's decision is Y. Was it input X that caused the model to predict Y, or was it one of the features in the input X that caused this prediction Y in the model? So I just want to point out that this kind of counterfactual explanation, they are mostly instance level, which is very much like similar to what Ryan wanted to do was interested in. Anyway, so basically, this kind of answering these kind of questions from pure observational data is pretty much impossible. We definitely need to know the exact equations and the causal graph for the data generating process. So it makes it impossible for us to do this from the pure observational data. On the other hand, there is a series of research that tries to approximate these counterfactual explanation from pure observational data by reformulating the objective of the counterfactual explanation into saying that it would be enough for us to generate an example that has minimal changes in the original instance's features, and results in like a different predefined output that's different from the original output of the model. And when we talk about the minimal changes, immediately we know that if we want these changes to be minimal and faithful to the data generating process of the example, we need to conduct these changes on the causal features. That brings us to the concept of causal feature selection and how we need to actually select and change these causal features to generate the counterfactual explanation. So basically, let's talk about have a more generalized data generating like a causal graph that explains the data generating process for pretty much any machine learning algorithm. So in this causal graph, usually what happens here is that we have a set of latent variables. Here we denote with Z1 through Zm, and they affect the generation of the variables that we observed in our input data, which here we denote with X1 through Xn. And through those like observed basically features, with like a combination of those features, we use them to do the final prediction, which we denote here with Y. So given this causal graph, if we would like to generate the counterfactual explanation, we need to answer a question, two different questions. How to identify, like basically we need to know what features to basically change and how to change them. What are the causal features and how we change them? So we formulate this in a two-step process. The first is to identify these latent features from the observed sample and from this data generating process. And the second step would be to identify what are the causal features responsible for the decision and how to change them. I just would like to take a moment to mention that this is actually very much inspired by the Pearl's framework of called counterfactual reasoning that has 3 steps of abduction, action, and prediction. The first step of the abduction corresponds to the identifying the latent features that affects the data generating process. And the action and the prediction corresponds to the second step of our algorithm, which is how to identify the causal features responsible for the final decision and how they will change the decision. All right. So because this talk is mainly tailored for the big era of big data and machine learning, I will demonstrate this concept through a large language model perspective, which are the state of the art in the NLP, and they have been shown to leverage billions of features to make their final decision. So as we discussed in the previous slide, we are gonna actually leverage the power of large language model to implement the two-step counterfactual explanation generation process. Our method is actually, so basically a step 2 and a step 3 pretty much are like, you can combine them in like one step. So in the first step, what we do here is that we say that given the input text and the predicted label from a black box classifier, we prompt the large language model to extract these latent or unobserved features that led to this prediction. Why is it like, what's the advantage of doing like using large language model here is that makes it actually very flexible. So traditionally, whenever we want to do latent variable modeling, we have to at least know how many latent features we need to have, or we need to have some sort of causal graph that actually explains the data generating process. However, when we leverage the large language model to extract these latent or unobserved features, there is literally no assumption on the data generating process or how many latent variables we have. We just let the model decide these latent variables and also leverage all the mechanisms that have been learned by the large language model to do this kind of inference. In the second step, we use the same large language model to identify the words in the input text that are associated with the set of latent features. So basically, this will tell us these are going to be the causal features that are faithfully represented in the causal graph that we had in mind and are going to be causal responsible for the final decision making. And finally, once we know what are these features and how we need to change them, then we just leverage the generating power of the large language model to generate the counterfactual text by actually explicitly ask the large language model to select a set of features from identified in step 2 to generate minimal change in the original sample, and at the same time lead to a different prediction or a predefined label that we had defined in our analysis. So this is an overview of our proposed framework. In the first step, what happens here is that we have the original input that we denoted with X. We have the prediction of the model, black box model, that we have no idea about the internal of that model. So we ask the large language model to extract latent features that result in this prediction. Then we get a set of Z's. Here we denote them with Z1 through ZK. In the second step, we already know what are these latent features. So we go back to the same language model. We ask it to identify the words. And the words here are basically, in the context of natural language processing, correspond to the set of features in the input. So we ask the large language model that given these latent features that you've extracted in the previous step, now you need to identify the words in the original input that are associated with these latent features and result in the prediction. Now that the outcome of this step would be a set of words that are basically highly correlated with the decision of the a black box classifier, and at the same time are faithful to the data generating process because they abide by all the latent features that we've extracted in the previous step. And then finally, we basically pretty much prune the decision of the set of features that we've learned in the previous step by asking the large language model to use or edit a minimal set of words that you identified in the previous step so that these words flip the label into the final prediction that we want to have. So these are the prompts that we've
Right,
used.
sorry, I'm really sorry to interrupt, but I think that this meeting only has a couple minutes. I'm not exactly sure how it works actually, but would it be possible to just
Okay,
give a summary or concluding remarks?
yeah, I'm actually pretty much done. I will just go over this and I will show you one result and we'll be done. I'll try to wrap it up as quick as possible. All right, so these are the prompts that we've used, pretty much what we've discussed in the previous slides, but in the form of prompt that are readable by the large language model. Finally, we evaluate the decision, the result of our algorithm. You can see that with different large language models, we actually achieve a very high performance in terms of the number of labels that we flipped at the same time. At the same time, the generated text has very high semantic similarity with the original text, both in the latent space and the token level space. So that means that we did achieve the minimal change constraint that we had in our counterfactual explanation generation. And at the same time, because we've extracted the latent variables, that actually gives us the faithfulness to the causal graph that we had. And these are the examples of identified latent features that we obtained using this framework. You can see that these are not the variables that you can quantify by just looking at the text, but refer more to the unobserved and confounders that we can't really quantify using by analyzing the text and the features in the text. And these are the other experimental results that we use the same counterfactual examples that we generated using this framework to basically analyze the performance of the large language models. And with this, I will just conclude my talk. I'm ready to take any questions.
Thank you for a lovely talk. Does the audience have any questions?
I have one quick one. In slide 5, if you go back there. Yeah, you taught in the generalization, you say models built upon causal features are shown to be invariant across different domains. I mean, I guess that's kind of intuitive, but I was wondering if you have any references for that, because I've been searching
actually,
for
so
some. Yeah.
This is a very good question. So this is actually built upon the principle of independent causal mechanism. So that principle tells you that once you identify the causal mechanisms, they are going to be autonomous and very much modular, meaning that if you intervene on different part of the causal graph, it's not going to actually affect the mechanism, the causal mechanism that you've learned in another part. So that means that if you can identify the causal mechanisms that are automatically built upon the causal features, those causal mechanisms are going to be invariant no matter what kind of intervention you conduct on the causal graph that you have. I can send you some references on this. There are a couple of papers published by Bernard Chekhov's group and Dominic Janzig's group. I can send you the references if you're interested.
That's awesome. Thank you.
I have a question. I might have missed it, but I was curious, how do you choose the causal features? Like, do you suppose that the causal graph is known?
Actually, so this is very much automatic because we are dealing with high dimensional text data and it would be impossible for us to know the causal graph beforehand. So we actually let the large language model to identify the causal features. So in the first step, we identified the latent features, completely automatic. We just let the language model to identify them. In the next step, we asked the language model that given those latent features that you identified in the previous step, now what are the features in the text that like basically have importance for this label predicted? So then that identifies the words in the sentence, which are going to be the causal features that we use for the final prediction. And then finally, once we have the features, we just ask the language model to set, like basically in the second step, it's still staying at the correlation analysis step. but it's more faithful to the data generating process because we have considered the effect of latent features. But in the third step, we make the final move saying that now among all these features that could possibly have a bit of correlation, select, use or edit a minimal set of words that you have identified such that they flip the label. So this is how we do the feature selection.
I see. Yeah, I'm less familiar with the data generating process to LLMs, but could you go back to a previous slide, the one with like cancer, like the Markov like rectangle? Yeah,
This one?
this, yeah. So I was thinking, for something like this, so you mentioned here, I quite like this graph, that the only ones that you should care about are the ones in red. Um,
Yeah.
and this, okay, I mean, this is, I guess, straight up impartial, but this made me think immediately of UMFI's blood relation axiom. Like the con would be that you would introduce blue. Like I was wondering if you think it'd be practical to use a method like that that would identify which methods have causal relations to the response. Or like I was curious, like what else you would use. I guess the large language model case is a little bit different.
Yeah, so in the traditional setup where we don't really have high dimensional like text data, there are a series of work developed for identifying the Markov blanket and Markov boundaries from the data. And they usually actually consist of like a forward and backward setting. So are you familiar with the causal discovery?
Yeah.
Yeah, so like identification of Markov boundary is essentially local Markov discovery. And what happens here is that you would like to identify that part of the causal graph that has like basically that like falls into that rectangle that you see on the screen. And what you do here is that you do like one pass of PC algorithm to
Yeah.
identify, the skeleton and the, spouse relationships. And then depending on what type of algorithm you leverage to do the Markov basically boundary identification, you can do a backward path to further get rid of the, unnecessary or redundant links that you have. But there are a series of algorithms developed for, only identification of the Markov boundary from the data. But the downside here is that none of them are applicable to these very high dimensional setups. Like, for example, text or image in which we use like possibly thousands of like features to do the final selection. And that's because usually the causal discovery or local causal discovery algorithms, all of them are very much time consuming and they're not scalable at all. So that's why when it comes to, high dimensional analysis, like for example, for NLP, large language models are going to be one way to go about these kind of things. But if you're interested in more traditional, setups and papers, I can send you some references.
Thanks. Yeah, no, that makes a lot of sense. Any last questions? Okay, I'd like to thank the speaker one more time and all speakers who presented today. And also, I'd like to remind everyone that we have a second session tomorrow at 6 p.m. Eastern time. And because we don't have a full lineup, if you think of any questions or points of discussion, please feel free to bring it up during tomorrow's Zoom.